Hello. Well, first of all, welcome, all of you, our staff members of the department, our students, and the students from all over the places, either in Istanbul and the other parts of Turkey. And it's my pleasure here to welcome our guest. But beforehand, I would like to thank our rector, Professor Naci İnci, for helping us to, giving this chance for us today to be with Professor Dame Joceyln Burnell to talk about the great adventure, actually, she faced through her PhD years. I know all about it. It was so exciting. I'm sure after she finishes her talk, you all feel the real life, how hard it was, and all students now, the graduate ones at the moment, maybe the future graduate students, actually will take a lot of lesson out of her talk. This was actually the purpose of my invitation of her to how to deal with the difficulties during the graduate PhD thesis and things like that, to be a good example and refreshing kind of, let's say, encouragement for all of you. So first of all, I would like to invite our rector, Professor Naci İnci. Please come here.
Ladies and gentlemen, esteemed guests, distinguished colleagues, and very dear students, it is with great honor and privilege that I stand before you today to introduce a true pioneer in the field of astrophysics, Professor Dame Joceyln Burnell. Born in Northern Ireland, Joceyln Burnell made a groundbreaking discovery as a postgraduate student in 1967 when she identified the first radio pulsars. This monumental achievement led to the Nobel Prize in Physics in 1974, although, regrettably, she was not recognized as one of the laureates. Her supervisor, Professor Anthony Hewish, received an award in her stead. Throughout her illustrious career, Joceyln Burnell has held numerous prestigious positions, including serving as the President of the Royal Astronomical Society from 2002 to 2004, the President of the Institute of Physics, I am one of the members, from October 2008 until October 2010, and later as the Chancellor of the University of Dundee from 2018 to 2023. In recognition of her exceptional contributions to fundamental physics, Professor Joceyln Burnell was bestowed with Special Breakthrough Prize in 2018. Rather than retaining the substantial prize money for this award, she made the selfless decision to establish a fund aimed at supporting female, minority, and refugee students aspiring to pursue careers in physics, a testament to her unwavering commitment to fostering inclusivity and diversity in scientific community. Notably, in 2021, Joceyln Burnell became only the second female recipient of the prestigious Copley Medal, following in the esteemed footsteps of Dorothy Hodgkin in 1976. from her formative years in Northern Ireland to her academic pursuits at the University of Glasgow and Cambridge, Professor Burnell's journey has been marked by resilience, determination, and a profound passion for physics. Her influence extends far beyond the realms of academia, as evidenced by her dedication to empowering women in science and her advocacy for scientific advancement in Northern Ireland. Most recently, Joceyln Bell Burnell's unwavering commitment to promoting gender equality in STEM fields was commemorated on Ulster Bank's new polymer 50-pound banknote, celebrating her legacy alongside other pioneering women in Northern Ireland scientific community. Before welcoming our distinguished speaker to the stage, I would like to invite her close friend, Professor Ercan, from our physics department about the importance of this talk for our undergraduate and postgraduate students. Finally, I would like to say that Professor Joceyln Bell Burnell is a trailblazer, a mentor, and a beacon of inspiration for aspiring scientists around the world, and we are very pleased to have her with us today. Thank you. I guess you want to say a couple of words how important this talk is for our graduate and undergrad students.
Hi again. Well, actually, I must tell you a few sentences about how I involved into astrophysics from actually quantum field theory, completely theoretical physicist in this department between 1976 and 1978, and an additional one more year to complete my courses, PhD courses actually. All of a sudden, by chance I must say, I entered without any purpose, with the encouragement of one of my friends, to an exam nation-wide, which is organized by actually Turkish National Education Ministry. And I didn't study at all because I wanted to be the first PhD student of the physics department of this university. Unfortunately, my precious early supervisor, Professor Mahmut Ortaçsu, then left us for his career to Germany. Anyway, after a while, I took the exam without, making any effort, just with my old knowledge, basic background, and so on and so forth. So, all of a sudden, I saw myself being the second-ranked student of this exam, which was a quite surprise for me. And then, anyway, I'm not going to talk too much about it. I didn't know what to do with it, but I must say something about, in this department, then there was a new fellow joined to our department, Ali Alpar, Dr. Ali Alpar then. I wanted to do my PhD in Europe. Well, of course, Britain was the place, since I didn't speak German or French or whatever, the closest because of some family reasons. So in a very short time, I found myself at Mallard Space Science Laboratory, which is subsection of Department of Physics and Astronomy of University College London, in year exactly in the mid of October 1979. So this is first time I went there. And my astrophysics or astronomy knowledge was zero. Anyway, we handled it. I got another MPhil degree by attending to the university department, so traveling a lot from where we live, then middle of the nowhere in a small village, to London almost every day. And then anyway, after finishing all these courses and so on, I was now capable of starting X-ray astronomy, which I have never heard at all before. So Joceyln was next door to me. I remember including one of my office mates, Dr. Graciela Brando Raymond. I must tell you that we lost her last year in November the 3rd, unfortunately. Especially her, Grazie, and Joceyln actually gave me a lot of encouragement. It's unbelievable. It would take hours and hours if I want to explain to you, but I will cut it short. So she's one of my role models. In fact, #1 over all my lifetime. So I am following her steps. But of course, I'm not going to be that breakthrough type of person anyway. My contribution, if it is even small or big, it doesn't make any difference to me, as long as we are working properly and doing our work, duties, and research, so on, in an appropriate way. So, thank you for listening. I would like to invite Professor Dame Joceyln Bell Burnell for his incredible, adventurous, what she says, the tale, but true story of her lifetime, which is going to be very exciting, I think you will find eventually. Thank you.
Good afternoon. Thank you for being here. I'm sure there are many other things you have to do, so thank you for being here. And thank you to the Rector and Nihal for your very generous introductions. This is a story from quite a long time ago. I'm going to give you a little bit about my background, and then I will tell you the story about the discovery of pulsars. One of the unexpected things about discovering pulsars is every so often somebody comes up to me and says, "You know, I nearly discovered pulsars," and tells me the story. These stories of discovery and nearly discovery tell us a lot about the way science works. And I will finish by talking about what I think are the factors that led to the discovery of pulsars then. So I started life in the north of Ireland. Politics in the British Isles is complicated, but a little bit of Ireland, northeastern Ireland, is with England and Scotland and Wales. It's part of the United Kingdom. The rest of Ireland is Ireland, the Free State of Ireland. And I was born and brought up in the British bit of Ireland. In Britain, every child had an important exam at about age 11 or 12. Because they believed that at age 11 or 12, they could see whether you were going to be academic or more practical. I failed that exam, so I should have been in the more practical stream. I should now be doing needlework and cookery, not science. But my parents protested, and they allowed me into the science class. The science class was about 25, 30 children, 3 girls, and all the boys. Boys had no choice. Girls had that much choice. We did physics the first term. I loved it. Without trying, I came top of the class. The teacher was very cross with all the boys for allowing a girl to beat them in the exam. Next term we did chemistry. That was okay. Third term we did biology. Here is a flower. Draw the flower. Label the parts. You've done that. Good. Here is another flower. Draw the flower. Label the parts. Learn the names. And I thought, biology. Boring. But I liked physics best. I had most of my senior schooling in England. This photograph shows my school in England. I had to live there. It was a boarding school. It was all girls, and sometimes girls' schools had difficulties getting science teachers. Our chemistry teacher, there was a picture of the periodic table up on the wall behind him. We'd say, "What's that? Why is it like this?" And he'd say, "It's a list of all the chemical elements." Why is it laid out like that? God made it so. He didn't understand the periodic table. The physics teacher was age about 80. He had come out of retirement a second time to teach us. He was a very, very good teacher. And I loved physics and could do it. And maths was okay. Chemistry, biology, no. So Northern Ireland is a small place, a closed community. And my parents wanted all their children to have some of their education outside Northern Ireland. So I went away to school in England. This is my boarding school in England. And there we had, yes, good physics teaching, chemistry teaching, okay. And I remember nothing about the biology teaching, so I suppose it was okay. But physics I liked. And in my senior years, my last 2 years, I did mathematics and physics, and more mathematics, and more physics, and more mathematics, and more physics, and that was great. I then went to do a physics degree. I was interested in astronomy. I was interested in radio astronomy, because optical astronomy you have to do at night. The sun prevents you from seeing any stars in the daytime. So you do optical astronomy at night. And I like my sleep. So optical astronomy, maybe not. Radio astronomy, you do day and night. So you can work office hours. Great. I am going to be a radio astronomer. And by chance, I think I end up in Cambridge, which is a very prestigious university, with very few women. Very, very few women. And in physics, very, very, very, very few women, of course. We, the women, were under a lot of pressure to be really good, behave well, do good academic work, so that the men would allow more women to come to Cambridge. And I think it worked, because now there are many more women in Cambridge. So the top picture is Glasgow University, and this is part of my college in Cambridge, where I spent 3 years working on a PhD. When I arrived in Cambridge, the first thing that happened was I was given some tools. These are the tools I was given. Day 2, I think it was, right at the beginning. This sends a message. Why do I need tools? What am I going to be doing with the tools? I am going to be building a radio telescope. There's a field. One day, Joceyln, you will have built a radio telescope there. The building took 2 years. We had to hammer a lot of posts into the ground, iron posts, and then mount wooden posts on them. By the time I had finished, I could swing what we call a sledgehammer, probably about 6 or 7 kilos, something like that. I was playing hockey, not ice hockey, field hockey. I could hit the ball from one end of the pitch to the other end of the pitch because of all this at work. It took 2 years, about 5 or 6 of us working for those 2 years to build the radio telescope. And this particular slide shows checking some of the cables. For the physicists and electrical engineers, there are some low-loss cables here. You cannot coil them up. You have to keep them straight. And so I worked in this little hut, putting plugs and sockets on this end, and in that little hut, putting plugs and sockets on the other end. And now we are checking that the electrical connections are good. For the physicists, there is a slotted waveguide here. And you can see we are working in the open and it's cold. That day it had to be dry, at least. This is the finished radio telescope. Maybe not what you think of as a radio telescope. It covers the space of 57 tennis courts. And it's working at 1.8 hectares. It's an interferometer. We used valves. Transistors were just coming in, but the professor did not trust them. No, noisy. No, unreliable. We use what in England we call valves, what the Americans call vacuum tubes. You know, things about this size. And every so often you had to check that they were properly seated. So it took us quite a long time to build it, 2 years to build it. Physically it is one, but electrically it was in 2 halves. So it's an interferometer with the 2 halves touching. The antennae are running along here. These is the feed wire, copper, oxidized copper, blue-green, into more lines and then into cables, and then away back 500 meters to the building where there were the actual detectors. How's this working? We are looking for objects called quasars. They were a very hot topic at that point. Radio astronomy had discovered some very strong radio emitters. They turn out to be very, very, very distant. If they're very, very, very distant, why are they so strong? They must be extremely powerful. They are what we call quasars, quasi-stellar radio sources. To the optical astronomer, they look like stars, hence quasi-stellar. But they have so much energy, they are not just stars. They are the compact centers of galaxies, quasars. There were very few known, and the purpose of this project is to find more. So, a little bit more physics. And I'm going to move. Can you still hear me? Great, good. Okay, so there is one of these quasars. It's way, way, way up there, millions of light years away. Here's the radio telescope, and this is material coming out from the sun. The sun is blowing out material, the solar wind. And the solar wind is not smooth. It has areas of high density, low density, high density, low density, high density, low density. For physics students, this is a diffraction grating. The waves can come through between, but they will not come through these bits so well. It is a moving diffraction grating because the wind is blowing out from the sun. And so some of the time the telescope sees through one of these, and sometimes it sees through a gap, and sometimes it sees through one of these, and sometimes it sees through a gap. And so the intensity you pick up fluctuates like this. This is about 1 second in time. If this is a compact object, if it is an extended object, like a radio galaxy, then the signal is sort of like that, and it's fairly boring. So the technique is to look for object whose signal fluctuates like this when you view it through the solar wind. That means it's a compact object, a quasar, whereas if it's a steady signal, it's a radio galaxy, and we're not interested in those. We want to understand the quasars. Our data came out on paper charts. The University of Cambridge had a computer, one computer. It had less memory than your laptop for the whole university. And it was not made with transistors, because transistors were very new and unreliable. It was made with vacuum tubes. And you had every so often to push them in again to make sure the connection was good. So the computer would have taken up all this stage area and have less memory than your laptop. So one computer like that for the whole of Cambridge University. For graduate students, no access, no. Our data came out on these paper charts. 30 meters per day. I scanned the sky every 4 days, so 120 meters for one scan of the sky, and then another 120 meters, and another 120 meters. And I observed for 6 months, so by the end I had over 5 kilometers, of this paper. Right, okay. So I'm repeatedly mapping the sky. We start looking at that strip. Next day we look at that strip, that strip, that strip. 4, 5, 6, 7, 8, 9, 10, 11 for 6 months. And I look on the paper charts for something that fluctuates. And that's a quasar. Easy. It's even a bit boring, but okay. So I did that, and remember, I'm scared. Cambridge is full of young men who talk about what Tolstoy said and what Pliny said and blah, blah, blah, blah, blah. And I'm a woman, and I come from the north of the country. I don't fit in. They've made a mistake. They're going to throw me out. But I'm going to work my hardest until they throw me out. And so I am working very, very carefully. And I find quasars, lots of quasars. But just sometimes there was something else. So maybe I'll go back a couple of slides. On this chart recording, we're now focusing on this middle bit. and it is what physicists call high-pass filtered, or low frequencies blocked. We have taken out all the slow wiggles, and we're left with the signals that are high frequency, because we're looking for this twinkling. So twinkles would show up on this. So this is a little bit of that center that I've just shown you. Here is the time, the right ascension. There's the date. There's a funny signal here that doesn't quite make sense to me. It's not one of these quasars that I'm finding, and nor is it the human interference that a big radio telescope will pick up. Here's a little bit of interference. So physics students, think about the difference between that and that. Here, the frequencies are lower. You can see through between the spikes. You can see the chart paper through the spikes. Whereas here, particularly this bit, the spikes are so close packed, it looks different. Here, the spikes go up and down, more or less equally. Here they go predominantly up. So this signal has different characteristics from that. Have some of you heard of Fourier transforms? You have just done Fourier transform in your head. You have looked at those two and said they look different. The frequencies are different, the amplitudes are different. That's Fourier transform. What frequencies, what amplitudes are present? Never mind the mathematics. That's actually what Fourier transforms are. So you've just done Fourier transform in your head because you say, this has high frequency, this has low frequency, this has positive spikes, this has positive and negative spikes. Or, put more generally, it looks different. So what's this? I asked my supervisor what this is, and he's not very, very impressed. I've gone the wrong way. He says, all that signal is crammed into 4 or 5 millimeters. We cannot see what's going on. It's all too compressed. We need an enlargement. When you're using chart recorders, enlargement is easy. You run the paper faster under the pen, and it all gets spread out. Enlargement. But I can't leave the chart recorder running at that speed all the time, because it gets through a whole roll of paper in 20 minutes. And guess who lives at the observatory putting a fresh roll of paper in every 20 minutes? No. Better idea. Graduate student goes to the observatory at this time, switches to a high-speed recording, lets it run to about there, switches it off, and the survey goes on as normal. And I did that for maybe 2 weeks, and I made high-speed recordings of receiver noise. The signal had gone away. And my thesis advisor was cross. Of course it's the graduate student's fault if the signal has gone away. Who else could be at fault? And then one day I got it. Along the bottom are 1 second time marks. Along the top, well, blip, blip, blip. Missing blip, blip, blip, blip, blip, blip, blip. These are equally spaced. 1 missing, that's still on phase. And look here, several missing, and then blip, blip, blip. And the spacing is about 1 1/3 seconds. I telephoned my supervisor in Cambridge. The observatory has to be outside the city so as to be radio quiet. So I telephone my supervisor and say, Tony, that funny signal, it's a string of pulses, 1 1/3 seconds apart. Oh, Well, that settles it. It's man-made. He thought it was human technology causing radio interference. Or maybe he thought his grad student was stupid. He comes out to the observatory the next day at the right time and watches me set up. This is scary because the source is not always there, whatever it is. There's been a spell when it was quiet, and then yesterday it was back. Will it be here today? It was, and he saw with his own eyes, pulse, pulse, pulse, pulse, pulse. And he agreed with me, it must be interference. But the stars take 23 hours and 56 minutes to do a complete orbit. It's because the Earth is moving. This signal was coming back 23 hours, 56 minutes later, or it was getting 4 minutes earlier every day. What human activity gets 4 minutes earlier every day? Only astronomers. Maybe it's some of the other Cambridge astronomers. Maybe it's those dreadful theoreticians. So he contacts all the Cambridge radio astronomers. Have you had a program going since September, blah, blah, blah, blah. No, of course we haven't. We wouldn't cause interference. So then we're scratching our heads. What is it? Well, maybe it's Joceyln wired the telescope up wrongly. Maybe it's something to do with that. So we ask a colleague who has another radio telescope working at the same frequency with its own receiver, could you help us by just taking a look to see if your telescope sees this signal? And I remember that day very vividly. The two telescopes were aligned slightly differently. My telescope saw that bit of sky first, and it was pulsing nicely. The student on the other telescope was called Robin, and so after we'd seen mine, we went over to Robin's pen recorder and stood by Robin's pen recorder, and nothing happened. It was quiet. And nothing happened. And my supervisor and Robin's supervisor started walking down this long laboratory. Now, what could it be that shows in your radio telescope but not ours? Could it be? No, it can't be that because, but what about me? And I was padding along behind. Robin stayed with his pen recorder. And suddenly there's a shriek from Robin, "Here it is!" And we all go charging back. And there's Robin's pen recorder going blip, blip, blip, blip, blip. Robin had miscalculated by 20 minutes when his telescope would see that bit of sky. If he'd miscalculated by an hour and 20 minutes, we'd have all gone home and the story would be different. But now it's seen the same kind of signal, same pulse rate, by a different radio telescope with its own receiver and its own chart recorder. It has to be something beyond the observatory. What? Don't know. But it has to be something beyond the observatory. And it's not Joceyln, and it's not the way Joceyln has wired up the radio telescope. My radio telescope is fine, thank you very much. So, you've maybe come across dispersion of light, when light gets spread out into a rainbow. Radio waves can get similarly spread out, although we don't see them with our eyes, but they can also be dispersed. And something that makes dispersion is electrons. So take a handful of electrons, and a radio wave coming through will get dispersed. The higher frequencies will go faster than the lower frequencies. So if we could see how much delay there was between the higher frequency pulses and the lower radio frequency pulses, and make a guess at the electron density in space, we could get the distance. And it took a lot of work. A colleague called John Pilkington borrowed 2 of my 4 receivers, tuned one of them up in frequency a bit, tuned the other one down in frequency, and after a lot of failed attempts, finally got blip, blip, blip, blip, blip, blip. And the delay between blip and blip gives you an estimate of the distance. Well, it doesn't strictly. It gives you an estimate of how many electrons are on the path between the source and your receiver. But we can make a guess at the electron density in space, and we can get an estimate of distance. And it turned out that this thing, whatever it was way beyond the sun and the planets, was far out in the galaxy. Still doesn't help us understand what it is, but never mind. Joceyln, keep on with the chart analysis, keep making these fast recordings. We want to see how stable the pulse period is. We ended up measuring the pulse period to about 8 decimal places. It's very stable. And so I start doing this, and one day I'm busy working through the backlog of normal chart analysis. Oh yeah, there. Oh, it's not it. No, it's not it. It's another one. Looks awfully like another one. Right, let's find the other charts from this declination strip, spread them out. The grad students worked in an attic. It wasn't quite as wide as this room, but it was probably as long as this room. And the desks were along the edge. And I would roll my charts out along the floor when I was doing this kind of work, and then line them up. So it's another one. It looks awfully like another one. And it's a totally different bit of the sky. Tony. Tony was never enthusiastic. So he told me I had to go and get a fast recording to see if this other thing was also pulsing. I did, and it was also pulsing. It was pulsing at, the first one was pulsing at 1 1/3 seconds. The second one was pulsing at 1 1/4 seconds. I did it just before Christmas. Went off the next day to my family for Christmas, leaving a note for Tony. Tony kindly kept the survey running, and when I came back, there was a huge pile of charts on my desk to be analysed, because that's the grad student's job. Tony's in a meeting, so I sit down, start doing this chart analysis. I'm finding lots of quasars, lots of good thesis material. Along we go. Which one's that? What? It's not either. Okay, there's only about another 3 meters of chart. I'll finish this bit of chart analysis, and then I'll come back and check up on this one. And so I do that, and Tony appears, stands at the end of the desk. Look, Tony, look. How many more have you missed? Go back through all your old records. I had probably about 8 kilometers of paper chart by that stage. I went back through the 8 kilometers, checking and checking and checking. And I could see that we'd detected this thing several times previously, but I just hadn't seen it, hadn't noticed it. It's Christmas time. I'm going on holiday. I'm going with my boyfriend, and my boyfriend in his baggage has a ring, because we're going to announce our engagement while I'm at my parents'. Tony agrees to keep the survey running. He won't do any chart analysis, but he'll put fresh chart in the chart recorder, and maybe even fresh ink in the inkwells. And I come back after Christmas wearing my engagement ring, which was stupid. Young ladies don't wear it to work. It gives the wrong idea. And I'm busy doing chart analysis. I come, which one's that? It's not either. It's not. Ooh. Now, I've only about another metre of chart paper to do, so I'll finish this. Hang on. What? I'm seeing double. Too much drink at Christmas time. At that moment, Tony reappears and stands at the end of my desk. Look, Tony. Oh, thank you for keeping the survey running, Tony. Look, look, look, look. I think there's 2 more. Oh. How many more have you missed? Go back through all your old records. There's about 5 kilometres of paper chart to go back through. I do go back through. I don't find any more candidates, but I do confirm these 2. And the 4th one is quite interesting because it's pulsing much faster. These 3 all have a period of 1 point something seconds. This one's going at 1/4 of a second. So it's going to push the theory. It's going to determine the model, this higher frequency, this more rapid pulsing. So we duly tidied all this up. We got all the data we could. We assembled it. I was still trying to keep up with the quasar work because I'm on a grant which finishes in September, and you know the feeling, not much money left. But we had 4. We published the first one first, and then said there's another few that will be in a subsequent paper. And Tony gave a colloquium in Cambridge just before the paper came out. We put it into Nature, which we judged was about the leading British journal. And there were 2 possible models we had at that stage. Either it could be something spinning, swinging a beam of radio waves around the sky, a bit like a lighthouse, or it could be something vibrating and somehow launching shock waves, giving pulses of radio emission. If it's something rotating, with age it slows. If it's something vibrating, with age the amplitude gets smaller, but the frequency gets higher. So seeing how the pulse period changed was important. Joceyln, keep observing these, all 4 of them, and keep the work going on your thesis. We managed all that, and then, as I say, we were about to publish the first one, and Tony gave this colloquium, and he favoured something vibrating. We gave the colloquium a very titillating title. Every astronomer in Cambridge came, including one called Fred Hoyle. Some of you may know his name. Fred Hoyle did not love the radio astronomers. Fred Hoyle's picture of the universe was what he called continuous creation, whereas the radio astronomy data was suggesting what we now know is correct, what's called the Big Bang cosmology. That a long time ago, everything was compressed in a very small area, and it went whoosh. That's the Big Bang. And the universe is still expanding today. And it's now well established that that is the correct model. But Fred Hoyle didn't like that. And anything he could do to show that the radio astronomers were stupid was good for him. So after Tony's speech, Fred Hoyle is the first to speak. And he says, I don't think it's an oscillating white dwarf star. I think it's a neutron star. In 40 minutes, he has absorbed all this information and hit the right explanation. He was an amazing physicist. At times he was a dreadful nuisance, but actually he was a fantastic physicist. And this was a good example of it. I don't think it's an oscillating white dwarf. I think it's a rotating neutron star. And right he was. We'd given some thought as to what to call these things, and apologies, this needs some subtle English. There were 2 possibilities: pulsating radio star or pulsed radio star. Pulsed radio star suggests there's something making the pulses, little green men. We didn't like pulsed radio star. So when a journalist said to Tony, "What do you call these things?" He said, "Pulsating radio star." No, that's far too long. What about pulsar? So it was a journalist who invented the name pulsar. I had a rough ride at that point. Journalists would not believe that a young woman was a scientist. I was a sex object. What were my bust, waist, and hip measurements, please? How many boyfriends did I have? Would I describe my hair as brunette or blonde? And why didn't I have it much longer? Young women were inevitably seen as sex objects, not intelligent beings, and certainly not capable of doing radio astronomy or discovering pulsars. So it was really a rather horrible time for me. But it didn't last forever, I must admit. One of the more sensible interviews we had was with one of the leading British newspapers, a very conservative newspaper, not one that I would normally buy, but it had a good science correspondent. And he said to us, "What are you going to call these things?" "Oh, pulsating radio stars." Much too long. We already had quasars. What about pulsars? So pulsars they became, thanks to the science correspondent of the Daily Telegraph. And that's the only advertisement I will give for the Daily Telegraph. How am I doing for time? Okay. One of the delights of having discovered pulsars is every so often somebody comes up to me and says, "You know, I nearly discovered pulsars," and tells me their story. And some of these stories are really interesting because they show how science works, or maybe how science doesn't work sometimes. The first one is a very long time ago, 1957. We are in the United States of America. We're at the McDonald Observatory, where there's an 82-inch, that's 2 meters, something like that, more than that, telescope called the Struve telescope. And it's the open night. The public have come in to see through the telescope. The telescope is set on the Crab Nebula, which is the remains of a star that exploded in 1054 AD. And indeed, you can see the remnant of the star. And the telescope is focused on the remnant of that star. And members of the public step up to the telescope and say, "Gee," or "Fantastic," or, whatever they said in 1957. And a young woman steps up to the telescope and says, "That star's flashing." And the night assistant explains about scintillation in the atmosphere. She said, no, that star's flashing. My job, she says, is to fly aeroplanes from the manufacturer to the customer. I fly at night. There's not much to do in the cockpit at night. I look at the stars. I know how the stars scintillate. That star's flashing. Nobody followed up. We do now know that star is flashing. Really quite fast, close to the limits of what the human eye can see. But people best able to see flashing at 30 times a second, apparently, are young women. It used to be the case in Canada that the mains power supply that provides the lights went at 30 cycles. And some Canadians, especially young women, could see the flashes. Canada ultimately changed to 50. But some people, especially young women, can see 30 hertz. So we think that young woman pilot saw the Crab pulsar flashing. But nobody followed up. It's only a young woman, yeah. In 2007, the Australians have an online pulsar catalogue, and they suddenly get an excited email from a rather elderly American called Charles Schisler. He worked for the United States Air Force, and he was posted to Alaska looking for missiles coming in from Russia. It was pretty quiet. And when it was quiet, his boss, his superiors, allowed him to play with the antenna that was supposed to detect the incoming missiles. And at night, or even during the day, he would look around the sky, and he found some things that flashed. He had done an astronomy course at college. He knew about the coordinate system, right ascension and declination, and he did the best he could to record the right ascension and declination of those flashing sources. He should not have taken that bit of paper away with him when he left the military, but he did. And he has just discovered the online catalogue of pulsars that the Australian radio astronomers keep, and several of his flashing radar detected thing are in that catalogue. He sent a very excited email to the Australians, and several of them, some of the more senior ones, quiz him, gently quiz him, but quiz him, and get all the information they can about what he did and so on. And they believe that he saw some of the pulsars long before, 10 years before. So he came to some of our conferences. It was highly confidential work, but he took a bit of paper away with him, recording the right ascension and declination. And lo and behold, they're in the Australians' catalogue, online catalogue of pulsars. Sue Simpkin. Sue Simpkin was brought up in Canada. In Canada, the power supply used to be at 30 hertz. And Sue was one of the young women who could see all the lights and things flashing at 30 hertz. She said it was horrible. It sort of drove you crazy. I could well imagine. Sue's going observing, and a Dutch astronomer, Lo Volcher, asked her to make an observation of that rather curious thing in the middle of the Crab Nebula. It's known as Minkowski star. Sue took an ultraviolet spectrum of it, said its spectrum was rather dull, but she could see the thing flashing. I don't know that Lo Volcher ever believed her. Certainly nobody followed up. You getting this message? Follow up. Even if you think that young woman's crazy, follow up. This is the last example. We're in radio astronomy again. Some radio astronomers are making a map of the whole sky, both hemispheres, using time on this telescope and that telescope and that telescope as they can get it. And they've nearly completed the catalogue. There's just some little gaps. And they're busy filling in the gaps. This is still the old technology. There weren't computers. They were using pen recorders and long rolls of paper chart. And one of the pen recorders was a bit sticky, troublesome. About 3 o'clock one morning, that pen recorder started going whoop, whoop, whoop, whoop, whoop. And the astronomer in charge thought, oh, damn it, it's that pen recorder again, and thumped it. That's how you cure sticky pen recorders. You thump them. So he thumped it, and it stopped going whoop, whoop, whoop, whoop. He had actually been observing a pulsar. And the point at which he thumped the pen recorder was when the telescope had turned away from the pulsar. So of course it stopped going blip, blip, blip, blip. He did not make an entry in the log book. Anybody here learning practical physics, practical chemistry, probably even practical biology, use your flipping logbook, write everything in it. You never know how important it might be. He had made no entry in the logbook. And sadly, when the discovery of pulsars was announced, nobody thought to go back through their data and see if they'd seen anything. But we're pretty certain that he had picked up one of the pulsars, 0329 plus 54, but couldn't get credit for it because he hadn't written it in the logbook. Following the discovery of pulsars, of course, they had all this sky survey data, but the collaboration had disbanded, and nobody went back through the records to see if they'd seen anything like it. They probably had. They may have seen even more pulsars than I had, but they missed out on that. I want to pay particular tribute to an Italian physicist called Franco Pacini. Some of you may know the name. Alas, no longer with us. He was a theoretician rather than a practical observer. And he'd studied in particular this Crab Nebula, the remains of the star that exploded, and the star in the middle. And he was wondering about why this thing kept shining, and said, well, maybe there's a neutron star in the middle, a neutron star with a large magnetic field, and the magnetic field is inclined to the spin axis, so the magnetic field cones around and irradiates the plasma of the Crab Nebula and keeps it shining 1,000, nearly 2,000 years, no, 1,000 years since the star exploded. He was absolutely right. There is this compact neutron star with a large magnetic field. Magnetic field is inclined to the spin axis, so the magnetic field goes around like this. And through magnetohydrodynamics, it keeps the nebula shining 1,000 years after the explosion happened. He was a brilliant physicist. So have I got another few minutes? Okay, right. Just want to reflect on what were the factors that led to the discovery, when it happened, where it happened maybe. I had my own telescope. I'd helped build it, and my own receivers. It wasn't shared equipment, and I understood how it behaved. I knew what was good behavior and bad behavior from that equipment. I'm a graduate student, a research student, working for my PhD. I don't have many other commitments. I do a little bit of teaching, but not many other commitments. And so I've got time and space to follow up anomalies and things I don't understand. I had a lot of things I didn't understand because I was suffering from what we call imposter syndrome. I was really overawed in Cambridge, more than I should have been, and that was actually limiting my performance to a degree, but I had time. We were using a very short integration time, 1/4 of a second. Previously, and still, radio astronomers were using 1 minute, something like that. And so they weren't seeing any fast fluctuations. They were averaging them out over that minute of time constant. But we were looking for rapid fluctuations due to the solar wind. And we weren't aware of other astronomers who might be working on this topic also. There was nobody breathing down our backs. So we could take a little bit of time to make sure that we were absolutely correct. We were 100% certain about what we said. University of Cambridge is a prestigious address. That helps people believe crazy results. If you come from some tiny little institution that nobody's heard of, they think, oh, stupid. But if you have an address like the University of Cambridge or an address like this, people say, oh yeah, they've got good people there. They don't do stupid things. We'd better read this. There's been a fashion in Britain for declaring what the objectives of your research are. You need to declare your objectives to get the money to do the research. We could not have declared this to be one of the objectives. Sometimes you get bad marks if you stray away from your objectives. Would the computer have given us bad marks? If we'd had enough computing power that we could have had the data analysis done by a computer, not by me, would we have programmed it to pick up this kind of thing? It was a bit outside the field I was meant to be working in. For a long time, low radio frequencies and fast time resolution were areas in radio astronomy that were neglected. Nothing interesting there. It has now changed, I have to say, which is good. And finally, just to amaze people who haven't come across pulsars, a little bit of their properties. A typical pulsar, a mass of 10 to the power 27 tons, but a radius of 10 kilometers. That's pretty dense, comparable with the density of the nucleus of the atom. A thimbleful of this stuff would weigh more than the whole population of the Earth. The gravitational force is very strong. The work you do climbing 1 centimeter on one of these objects is like the work you do climbing Mount Everest here on Earth. And the atmosphere is similarly compressed. Strong gravitational force bends light, so you can see over the horizon. Gravity also redshifts light, so if we were present on one of these stars, our body color would be redshifted. Little green men is typically what we talk about as a joke. And the gravity also affects clocks. Clocks go slow in strong gravity. So 1 second would take 2 seconds, in fact. There's a very strong gradient of gravity. The gravity at your feet is much, much stronger than the gravity at your head on these things, and so your body would get stretched. They've got huge magnetic fields. If you spin a magnetic field, you get huge voltage drops, and so you end up with a huge Lorentz force as well. Don't go to one of these, however attractive the trip sounds. It's not good for your body. All that manages to rotate like a solid body, and we now know that the pulse period is the rotation period. And we see some pulsars with periods of just a bit over 1 millisecond. So they're going 1,000 times a second, or maybe 800 times a second. They are really rather weak radio sources, but you can do the timekeeping good to 1 part in 10 to the 23, which is phenomenal accuracy. And so they're being used to check out, for instance, Einstein's theory of relativity. They're very, very good clocks. We've still got some things to solve, quite a few things to solve, but that's great. And let me finish there, and thank you for your interest. Thank you for your attention.
Joceyln, for your inspiring and fascinating talk. I wonder if there could be any questions from the audience. Yes, please.
There's a microphone coming to you. You don't need to repeat the compliments again.
What sparked your attention to the astronomy? Because you were already good in physics, you could have chosen another field in the physics. What did spark and kept your motivation when you do all those hard work? And if it's okay to ask, I have another question. I wonder how you balanced while you do this much academia and with your family, and especially when you were a mother. How did you balance?
Yeah.
Thank you very much.
I'll deal with the family bit first. We have one son who is now a physics professor in solid state physics. I think my husband found it hard because the pattern in Britain is that the man, the big man, you know, is everything, and the little wee woman, you know, keeping house. And I clearly was not in that role, so I think he found it hard. And in fact, the marriage didn't last. But my son is a physicist, so yeah.
And your grandson is on
Sorry?
the way. The grandson is also on the way.
Oh, two grandsons, but neither is a physicist.
Oh, okay. Any more questions?
Also about the astronomy, what sparked your
Sorry.
attention to that?
Yes. My father was very widely read and had fantastic general knowledge, and brought home books from the library to read and would leave them sitting beside his armchair. And I would look at these books, and if it looked interesting, I took it away to my bedroom to read. And Dad would say one day, "Where's my library astronomy book, Joceyln?" So I think once he knew I was interested in astronomy, he brought home astronomy books quite a lot. But even so, he was very encouraging, and was keen that girls did science, fought for me to get to do science at school, for example.
Thank you very much.
Questions? Yes, please.
There's a microphone coming to you.
Were you able to hear what I said before?
You were wondering how I felt, especially at the beginning?
At the beginning, when you were unrecognized for your research, and how was your path to the recognition, and how did you keep your motivation and persevered in your research, I guess, in the meantime?
Yeah. There were actually two factors. One was my husband's feelings. He didn't like it that his wife was doing unwifely things and being famous, you know. So ultimately the marriage broke up. It was difficult being married because you're looking for jobs, good jobs for two people in the one place. And he felt he had to move every so often. He worked in what we call local government, you know, the city area, something like that. And he would be there for 5 years, 8 years, and then he'd say, "It's time I moved." And so we would maybe go, there. So I went from radio astronomy to gamma ray astronomy to X-ray astronomy to millimeter wave astronomy because of my husband's moves. Crazy career. Not a career, but fun and interesting.
Any more questions? Yes, please.
So first of all, again, thank you for this inspiring speech. I'm wondering that you mentioned if you had a computing power that much, would we be able to find it? Because nowadays, physics also going through that computational things mostly. And I know in Oxford you have AI for Science Lab, which they are also doing some stuff. So my question is that, do you think as a physicist, are we ready to use that computational data to be able to do some breakthrough? Because we have too many power now, it's computation, but are we looking to right things while doing it?
Are we looking for the right things? You don't know that until you found something. It's only afterwards you know you're looking for the right things, for sure. But you can make a good guess. I mean, I think you should look for a whole range of periods or timescales of changes. I think you should look at a whole range of frequencies. A lot of the work has concentrated around the 21 centimeter line, which is a line from the neutral hydrogen atom, because there's hydrogen everywhere in the universe. And if we wanted to signal to them, it's quite a sensible frequency to choose because they'll know there's lots of hydrogen as well. But yeah, it's complicated. We're doing quite well. Computing power has increased enormously, of course, which does help. You couldn't do it without computers, for sure.
Thank you.
Okay, let us thank Joceyln once again.
Thank you very much. Thank you.